let's do a couple more examples of calculating the area based on polar equations. So example number 2 from our lecture notes says the equation of a circle of radius r centered at the origin is the equation little r equal capital R. So essentially, let's just assume we're dealing with the equation of a circle, and we want to know the area within the circle. It says prove, of course, we know the area of a circle should be pi r squared, but it says prove the area of such a circle is what you'd expect by integration compared to the rectangular equation x squared plus y squared equal r, or parametric equation x equal r cosine theta or t, and y equal r sine t. So let's just kind of play around with doing the area in each of these formats and make sure the answer is what we expect it to be. So let's start with polar, because as we can see, the equation of a circle is very, very simple in polar form, as you know, we looked at a few videos ago, and it turns out it's very easy to do in this case, because you know, we know that the area of a polar equation is the integral of 1/2 r squared d theta, as theta goes from, well, whatever region we want to do. And you know, examining the a circle of radius r in polar form, in order to integrate across the entire curve to find the area enclosed within it, we know we'd have to do a complete cycle of theta going from 0 all the way to 2 pi. So in order to calculate that of a circle, we need to integrate from 0 to 2 pi of 1/2 r squared. And the equation of a circle of radius r is just r, whatever constant is, so we'll replace this with capital R with respect to theta. And if we're dealing with just basically this is a constant function, we know that the integral of a constant and of course 1/2 can be pulled through the integral symbol, and that will give us 1/2 r squared integral d theta as theta goes from 0 to 2 pi. And essentially we have the integral of 1, or you know, obviously we don't have nothing, but the integral of nothing is c. But in the context of definitely, well, you know, if we factored everything through, of course, there'd be a 1 remaining. But we know the antiderivative of 1 is just theta, and so that's what we'd end up with, theta integrated from 0 to 2 pi. And now plugging that in, of course, what we get, of course, we have the 1/2 r squared out front as well that I've currently lost track of. But we get 1/2 capital R squared times theta evaluated from 0 to 2 pi. Of course, 0 would be 0 and 2 pi would be 2 pi. So what we're going to have is 1/2 r squared times 2 pi. And of course, that leaves us with pi r squared. And so, you know, what we get is an answer that we'd expect. And this is just a good example because it confirms that the formulas that we're using based on certain equations of certain types, you know, give us the answer we'd expect. And of course, if we were to solve the same problem, we could do it in rectangular form. And we could do it in parametric form, and obviously we should be getting the same answer. So let's kind of compare. Let's say we were to do these things in another form, just sort of by a comparison. Let's say we wanted to do use the rectangular equation instead. Well, we need to solve for y in order to do that. So, you know, the equation of a circle would be, you know, we get y squared is equal to r squared, capital R squared minus x squared. And we would have y is equal to plus or minus the square root of r squared minus x squared. So let me fix my square. Came out a little funky. And essentially, the equation of a circle, it's not a function, but we could break it into two parts. The positive root of r squared minus x squared and the negative root of r squared minus x squared. And really, we could imagine integrating this from negative r to r if we wanted to find the area under the curve, right? Because if it's done, if we're using a rectangular equation as a function, we would integrate from x, you know, which would be from here to here, negative r to r. And so essentially our area, I'll just write the area of the top would be equal to the integral of negative r to r of the square root of r squared minus x squared with respect to x. And what we're going to have is a problem that's going to involve trigonometric substitution, because in order to integrate you know, the square root of something squared minus something squared, we know that, you know, the process for doing this would involve trig sub. And similarly, the area of the bottom would be equal. So what we could just do is say the area of all of it is just equal to twice that. So area of this full circle would be twice that amount. Or you could integrate the lower and upper part of the curve separately, but that's, of course, going to be a waste of time. So anyways, the substitution we would need to do here would be x is equal to sine of r sine theta. You know, if we're going to do a trig sub, x equal r sine theta. And that would leave us with dx is equal to r times the cosine of theta d theta. And so, you know, of course, we could continue to solve this. This would leave us with twice the integral from negative r to r of, well, we'd have r squared minus r sine theta quantity squared, which would be minus r squared sine squared theta. And d theta, we'd also have multiplied by r cosine theta d theta. Now, also, I would need to change my boundaries in terms of theta. And if you're wondering, okay, how would theta work in this particular instance, notice now I'm in a series of coordinates that are involving theta with respect to sine theta. And if I'm thinking about, you know, how would negative r to r change in terms of theta, I would want to look at this equation, which would be x equal r sine theta. So let me go ahead and change the boundaries because that's how I prefer to do trig sub. And so r equal r sine theta would imply sine theta needs to be equal to 1 on the top half. So sine theta is equal to 1 at pi over 2. So that should be the top end of our boundary. Notice it doesn't correspond to the polar coordinates at all because we're dealing with completely different procedure. And in order to do negative r in our substitution equation for x, we'd have sine theta is equal to negative 1. And so that would be at minus pi over 2. And progressing a little bit further, well, we're going to have, we could factor through the r squared through the square root, which would give us r. We have another r, so we could pull that 2r squared through the integral. And this would leave us with the square root of 1 minus sine squared times cosine theta d theta. Of course, the square root of 1 minus sine squared would leave us with cosine squared or cosine, and we end up having a cosine squared. Theta with respect to theta. At this point, you can see quite clearly this process of solving the area within a circle is much, much more complicated. And I believe we may have even done this or a similar example back when we were talking about trig sub. But it brings up an important point that using a different coordinate system can be stupendously simpler than trying to use rectangular coordinates. And circles and similar types of mathematical objects are much easier to use polar form. So great example. We're almost done, so let's go ahead and finish it. But we could, you know, to integrate a cosine squared, we know we need the power reducing identity, which would be 1/2 1 minus cosine of 2 theta. So this would, we would have twice r squared integral from negative pi over 2 to pi over 2 of 1/2 1 minus cosine 2 theta with respect to theta. Or is it plus? I do not remember because I think sine theta is plus. The power reducing identity is one that for some reason it's very easy to forget because the difference is just between a plus or minus. So let's pop up you know, and obviously in the real world, whenever if you ever forget an identity, I would always recommend looking it up if you are worried that your memory is failing you. So let's go ahead and pop up my identity sheet, make sure I am using the right one. And yeah, cosine squared is positive. So my gut told me I was wrong, and my gut was right. My original self was wrong. Anyways, integrating, we're almost done. Of course, we could cancel the 1/2 with the 2. And the integral of 1 is, of course, theta. And the integral of cosine 2 theta is sine theta over 2. Sine 2 theta over 2, of course. Evaluated from pi over 2 to negative pi over 2. And, of course, now if we plug these things in, sine of pi over 2 becomes sine of pi. These are both going to be 0. So what we're going to have is r squared pi over 2, and then minus r squared negative pi over 2. And of course, plugging sine in, both of those went to 0, which is why I skipped that. But plug in pi over 2, subtract negative pi over 2. What that leaves us with is pi r squared over 2 plus pi r squared over 2, which is, of course, pi r squared. And we get the same answer. And, you know, that's another moral of the story from this example is integration sometimes is very terrible. But if you take a different approach, much, much simpler, can make your life a lot easier. And let's go ahead and just set up the parametric equation, and I'll leave it as an exercise for you to try on your own. But, you know, again, we also have the parametric equation of a circle, which is x equal r cosine theta, or t, and y equal r sine t. Or most people would probably use theta over t, but at the end of the day, it doesn't really matter. And similarly, we could view this equation as an integral of the parametric equation across a full circle of a full interval of 2 pi. So, you know, setting up the integral again, the integral of a parametric equation would be alpha beta of gt times f prime of t with respect to t. Or y multiplied by, whoops, you can't see what I'm writing, y multiplied by dx dt dt. And again, also, you know, remember that this kind of, another way of thinking about this is why this makes sense, is because if you think about it, well, you just have y dx and the dt's would cancel if we're thinking about it with Leibniz notation. And we would just integrate the area under the curve as normal. But if we're thinking about the polar equation, well, g is just r sine t. So we'd have the integral of r sine t. F prime is the derivative of our x equation, which is also going to be, well, it's negative r sine t. And all this integrated with respect to t. And if we just integrate from 0 to 2 pi, that should cover the full period of the parametric equation as well. Or you could use the x components and do it as 2 separate integrals from left to right, but we'll just go ahead and go from 0 to 2 pi. And a reminder, this could give us the wrong sign. The answer could be negative if we're going clockwise versus counterclockwise based on the direction of the parameter as it flows, as we saw in a previous example. So if our answer ends up being negative, we know that we probably just should have set it up in the reverse order. But let's not waste our time trying to figure that out right now. So we could pull the negative r squared through, and what we'd be left with is integral from 0 to 2 pi of sine squared t dt. And this is something where let's just go ahead and use our calculator so as to not waste more time, but it's almost exactly the same integral as we just solved. So integral of 0 to 2 pi of sine t squared, or what theta, I'll just leave it in terms of theta. No need to change it. Make sure my calculator is in radian mode, which it is, and if it was not, that would be completely wrong. But what I end up with is an answer of 3.14159, obviously pi. So what we get is, you know, when solving the area of the circle parametrically, I get, well, negative pi r squared. But as I was saying, kind of expected this answer to be wrong because it was going counterclockwise, where clockwise, if your parametric equation is moving clockwise, your area is treated as positive versus negative just based on the setup. But anyways, we're going to get pi r squared or negative pi r squared. Of course, we know that's because of boundaries. Anyways, that will wrap up this video. In the next one, we'll do, actually, I'll leave this example of the finding the area within the rows of 4 petals, the same equation that I left for you to graph. Actually, well, whether it's sine or cosine, it doesn't even matter. But, you know, you can use this equation or you can try for this one and think about trying to do it on your own. In the next video, we will talk about arc length in both parametric and polar form.